Today we're going to be talking about second order systems and higher order systems. We're going to start with second order and discuss a system in which we have x of s becoming z of s becoming y of s. Now in between, each transfer has a function k1 over t1s plus 1 that leads to z of s, which then goes into k2 over t2s plus 1 that makes y of s. Now, the overall transfer function of this would end up being based on the series operation, the multiplication of k1 over ts plus 1 times k2 over ts plus 1, yielding total k1, k2 all over t1s plus 1, t2s plus 1. Now, if we think about how that would be expressed if we pulled it out entirely, we would get something at the very bottom like this, where we have a total gain for our system, and then we have time constants that are together with some dampening function that would overall be used. And its damping coefficient is often expressed in the ODE form here, which could be found in pink. So really we can make this model go a little bit more deep. We could have time delay factors like e to the negative s theta involved inside of this. We can have other numerator dynamics like s plus 1, but for now we're assuming just a standard response. So what if we had a step response behavior as a way of then modulating out what would happen with x of s? So in that case, let's say we had a step function. If we had a step function where we had a standard x of s is equal to delta x over s, where ultimately that would mean that by the inverse Laplace, x of t is delta x itself times the step function del t, then in this case we would take this function g of s would be equal to, be multiplied by x of s to yield y of s, which would be in this case our full function kp over tau s times tau plus 2 tau dampening function s plus 1, all multiplied by our delta x over s. So in this way, we would then combine this to yield kp delta x over s t2s plus 2t dampening s plus 1. And now if we computed this then based on its roots to see where we have maybe a real root or complex root from our second order polynomial, we can ultimately find the direct roots of the system based on solving for s roots using the quadratic equation. And in this case, we would say that this is equal to negative b plus or minus square root of b squared minus 4ac all over 2a as per our standard quadratic formula. But on this specific equation, this is now stating where a is equal to tau squared, so a, and then we also have b, and then we have c, based on what we're actually solving for in that equation, which could also be found, funny enough, based on our original ODE form essentially. But in this case, we're solving for it directly right here, which b is now 2t c, and then c is equal to 1. So if we plug that in to solve for our s functions with our roots, we would get minus b, which is 2 tau c, plus or minus b squared, 2 tau c squared, minus 4 times tau squared times 1, all over 2 tau squared. So when we solve that out, we would essentially get minus c plus or minus the square root of c squared minus 1 all over tau. And therefore, what we're really looking for here when solving for this equation with our roots is that the value of our damping coefficient is really going to help to determine if we have a real root or if we have a complex root. And now in a stable system, therefore, we would want to see where maybe c extend to be greater than 0. Otherwise, one root will have to be positive in a real part that will lead up to blowing an exponential in the time domain. And so based on this, and assuming we have a stable response, we're really looking for 3 potential systems of how we would describe this being on an overdamped, critically damped, or an underdamped condition. And ultimately, now that we've solved for these roots that might exist in S, we're able to see that with this equation, we're really now looking for what's happening inside of the square root specifically. And now C is going to affect that regardless. But on the same vein, we have three potential conditions that we want to study. We want to see where maybe we become overdamped, where C is greater than 1. Because in that case, this is looking like it's going to be much greater than 1, and the square root inside is going to be thus actually greater than 1 or positive, and we have real numbers with distinct roots. Now, if it's equal to 1, then inside the square root, we're going to have 1 squared minus 1, which is just the square root of 0, and thus that is 0. So we're really just looking here at real and repeated roots on C. And then if we have between 0 and 1, that's going to lead to an underdamped system where ultimately we will be getting some complex conjugates. And now in that case, we are going to have to consider what's actually going to happen based on looking into poles and zeros for an underdamped complex system where we would then need to complete the square. So I'm going to erase part of the board now that we've walked through what a second order system would look like, in which you have series-based functions, and we're going to then try and describe each of these conditions and what they might look like for you. Remembering our response types that we had below, I've now just expressed them here on our three different conditions. We're going to work out the conditions to the right over here. So in an overdamped condition, C is greater than 1, so our damping coefficient is greater than 1. We could see that our standard equation that was inside of that in the denominator for our transfer function was ta squared s squared plus 2 ta cs plus 1. And now when it's equal to an overdamped system, that's extracting back out from what our standard denominator would look like for both transfer function 1 and 2, which had transfer function of time 1, so t1s plus 1, and of 2, so t2s plus 1. Now if we expand this term, we get t1 t2s squared plus t1 plus t2 times s plus 1. And now because this is equal to that, based on the same grouping of terms, our s squared, our s, and our 1s, we have coefficients that must be equal. Though, looking at them, we see that generalized time squared is equal to time 1 times time 2, and t2c is equal to t1 plus t2. So I've gone through and I've already rearranged what these would solve for then, and we see that we have both of our time constant conditions where it would hold for any overdamped system that is greater than or equal, in that case, to 1. Now, remember, critically damped is when it is in fact equal to 1. So say you did plug it in for 1, you would end up finding that you just solve back for the critically damped condition. So this would hold true, but that's only because of the denominator term, our square root specifically. So in that case, say they wanted to verify that this is the correct one to solve for. We can plug this back into the previous expression where before, in how we were solving it, we would have seen, I'll actually use a different marker, I'll use the orange one. We would have seen that y of s, which was g of s, x of s for our step function, is in fact kp delta x over s times t1 s plus 1 times t2 s plus 1. And that would be true then for an overdamped system where we have different factors of t1 and t2 of which we are specifically solving. And so if we wanted to then determine the domain expression using an inverse Laplace transform for this, based on our actual solutions that we already have explicitly now for t1 and t2, this would ultimately then go back into a derivation that would solve for, using the table directly, now y of t, which is the inverse of y of s, is kp delta x times 1 minus t1 e to the negative t over t1 minus t2 e to the negative t over t2 all over t1 minus t2. And this would hold true for conditions in which t1 is greater than t, which is greater than t2, allowing this to end up becoming a true statement ultimately. And notice that in this case, the time response is dominated by the slowest time constant, which is this one. because it's the greatest amount of time, it's the slowest time constant. And we would use the table directly to solve that one. Now, if we went into a critically damped solution, and yes, we can use the table once again to solve this one directly, we would see that this would be in the denominator. So our y of s here would be kp delta x over, and we would replace that term with our standard expression here, s times ts plus 1 squared. And this has a standardized solution for its inverse Laplace to give y of t equal to kp delta x times 1 minus 1 plus t over tau e to the negative t over tau. And now in this case, we still are seeing the conditions that t1 is going to be greater than t for the case of a standardized solution that's overdamped, as we've just previously described it. However, in the same condition though, when we're looking at a critically damped solution, we know that this has to be faster than the overdamped solution. This would mean then that in this case, we do allow for this to become equal. So in this way, we are seeing the potential condition that T1 is ultimately going to end up being equal to T2 times T. This is a perfectly or critically damped solution. This is going to be really our fastest type of solution that we're looking for in this case. So what would happen then in an over-damped that leads to a critically damped that leads to an under-damped? So especially if we're now considering the fact that we might have a complex root, that is going to be something that involves completing the square. So completing the square from our previous lectures allows us to say, okay, well, we have as squared plus bs plus c. And if we wanted to solve then for how this could be rearranged, that would end up being the square root of a times s plus square root of a times b over 2a all squared plus c minus a times b over 2a squared. This would essentially be a solution for s and allowing us to then see how this function could be rearranged. And this then could be used directly where a is equal to tau squared still from our original term that we're looking for all the way up here. B was still 2 tau c and c was equal to 1. And plugging in those terms there for completing the square, we're able to solve and yield this expression. And now if we were then to plug it into the solution for previous cases, we would see that in just the same way as how we're having a solution that gets plugged directly into the denominator, we would see this become y of s is equal to kp delta x over s times this piece. So tau s plus c squared plus the square root of 1 minus c squared squared. And that would end up being our solution directly for seeing y of s based on the step function that we're using in x of s and evaluating this potentially using a Laplace transform. So we can either use P of E or we can use the table to ultimately solve for the inverse, where y of t now is going to be a very large expression that I hope I can finish over here. Just to be safe, I'm going to go ahead and write it down here as y of t is equal to kp delta x still, because that is our total gain that we've achieved from the system again, multiplied by 1 minus e to the negative dampening coefficient times time over tau, multiplied by cosine of, we're going to say wt plus dampening coefficient over the square root of 1 minus c squared times sine of wt, where w, I'll write it here, where we're going to redefine w as the square root of 1 minus c squared over tau. And that is going to be the frequency of oscillations in our system. And so if you notice, now we have this solution that involves both cosine terms, sine terms, we have our exponential term here, and we're using omega or w, where in this case that is equal to the square root of 1 minus c squared over tau, giving us the number or frequency of oscillations that are used in our decaying oscillations. So these then would be the three base solutions that you would have for describing a second order system, which are all based on the potential use of a damping coefficient that would ultimately exist for that solution. And so I'm just going to circle all three of them, and that these more or less become the ways in which you can then derive this and equate how you would solve your output based on your input functions. And again, this would be in a series-based system in which you have two different pieces going in, and you have to consider how the time is influenced by both of these conditions independently. And this just helps you to relate the times at which they move and how you can dampen the relationship between them. So next, we're going to go through and walk through the potential of solving for poles and zeros using an analysis of higher order systems. Let's discuss some higher order systems that we can converge on. Linear ODEs without time delays often and pretty much always will have a transfer function that could be built upon a ratio of polynomials. So we've discussed this before in that we can have g of s based on a numerator function over a denominator. We've been calling it oftentimes y of s over x of s. And as before, it could be the sum of I from 0 to m for bi times s to the I, where we can then describe the function here in the numerator. We could do the same thing in the denominator with our coefficients of a going from 0 to n for these. And now when we consider rewriting this standard solution that we had from before in its pulse zero form, we're going to take the numerator and we're actually going to pull out the expression of just the max term bm. We're going to do the same thing in the denominator term for an, and what we find is that for the first term, well, that's now 1 times s to the m. But for the second term, in all the preceding terms, it will be divided by b to the m. It's a coefficient number. So we can then rewrite this entire form as bm times a function of s minus z1, where those are zeros, multiply them through each for their own specific z functional terms. And that is going to maintain truth. Now, additionally, we could do the same thing in the denominator, but we're going to use a different term, p1, for the poles. And rewriting our transfer function from before, where it was this, we now have a new numerator term, which is this bm with our zeros, which is going to be here, divided by our denominator term, which is our an with all those poles, given here. Now, in the front of this, we have bm over an. That's just going to be a standard constant. But I do want to point out that that's not the same thing as gain. So traditionally, we can get the gain by taking the limit as s goes to 0 for g of s, which would ultimately be b0 over a0. But that's not necessarily true here because this zeros and poles form is not going to actually give us the gain in front directly. We'd have to solve for that through. But in rewriting it in this form, we can see the list of terms that describe the zeros of our function in the numerator and the poles of our function in the denominator, where the poles are ultimately going to be what's going to give the stability of our system. So let's describe how this is in fact important. To this point, we've been using a lot of step functions, where ultimately by applying a step function for our input, we should see a proportional change to our output. We're just tracking how it gets there mostly. We're modeling about how it's going to get from one point to the next. But say that we use impulse, for example. Impulses, again, are going to be these delta functions. My delta looks pretty bad. And that's going to be equal to, say, 1. And so for our delta function, if we had y of s equal to g of s times x of s, and we subbed in our impulse, which is this delta t equals 1, then that would mean that we'd have g of s times 1, or just g of s. And so that means that we should directly have the same return. It should not be changing or moving, it should actually return back to its standard function, where y of s is equal to g of s. Now, we've applied an impulse, but it should go right back as it would have before. But if we do not have stability, then it will not return. It's actually going to mediate away from that, and it's going to be blown off course. That would mean that we don't have a stable system, and it should not then return back to 1, even though that's the goal of what we're trying to see. So one way to quickly evaluate this based on the stability would be the poles in our system, of if it can return back and how. So that again goes back into the denominator term here for the poles that might exist in our solution. So say that we wanted to describe this in terms of a pole-based system, we would want to say, well, we have this function here, which we can rewrite as g of s is equal to c times s minus z1, s minus z2, and so on until s minus z of m, and we're going to divide that by s minus p1, s minus p2 until s minus p of n. But we can use our partial fraction expansions to actually rewrite this equation entirely by setting equal to alpha 1 over s minus p1. Notice our pole is what we're using because we're going to rewrite the numerator based on those alpha terms, plus alpha 2 over s minus p2, and so on until alpha of, in this case, n over s minus p of n. Based on the number of poles that we have, we'll have a proportional number of alpha coefficients that we would use to resolve. And in solving for that expression, we would then actually find those alphas, and we could take then the inverse Laplace directly to get a g of t, which is really our y of t function here. And that would be equal to inverse Laplace of each of these specific terms summed together, alpha 1 e to the pole t plus alpha 2 e to the pole 2t, and so on until alpha n e to the pole of nt, where y of t is equal to the sum from 1 to n for alpha n e to the pole n of t. And this should actually look pretty familiar, especially here when we talked about those poles before. We were really talking about this term, if you remember. I specifically said at one point we can consider the pole as like s plus minus p, or we can think of it as s minus p. One or the other, they look the same, but we're really looking to see if the pole is negative, how that impacts stability versus if it's positive or zero. And we're really just saying here that now instead of e to the negative t's, we actually now can use p directly for the pole value itself, which is equivalent in this term. So this is actually really cool to see that we've been able to resolve this based on our poles, but this again is based on the fact that this is a mode process for each pole. We need real functional values for each of these poles, specifically where the system is then going to be stable. And so if we have real values for all of these poles, then these will allow us to be in a stable solution if those poles are all less than 0, as described before. We need those to be going back down and converging on a value. Based on an understanding of this, let's try walking through an example so that we could determine our poles and our zeros based on time functions using a standard transfer function. So remember, g of s specifically is going to look like c times, we have s minus our zeros over our poles. And say that we're given the fact that k is equal to 5. We're going to have 1, 0, which is going to be z1 equals 1. We're going to have two poles where the first one is -1 and the second one is -2. Let's try evaluating the system and looking at it more deeply. So we know that we have g of s now equal to c, some constant that we want to solve for, multiplied by s minus our only 0, which is 1, over our poles. So s minus the first pole is -1. That's going to end up being minus -1 or plus 1. And s minus our second pole, it's -2. Therefore, negative of -2 is going to be plus 2. Let's take k to be the limit as s goes to 0 for g of s. That is c times, if we plug in a 0 here, -1 over 0 plus 1 is 1, 0 plus 2 is 2. Rearrange. C is now, if we multiply by -2 on both sides, -2k, or -10 if we plug in the 5 for the k. So we can rewrite g of s as -10 s minus 1 over s plus 1 times s plus 2. And that would be the transfer function here for our system, where we have our 0, we have our two poles, and we have our c value. But let's say that we wanted to now rearrange this so that we're always in the s plus 1 notation so that we can extract out our time functions for our zeros and our poles. So in that way, we are going to want to take this specific one term and we are going to want to try and multiply by 1/2 over 1/2, which is really just a 1. That will help us on that term and be able to be used directly. Now, on this term, we're going to want to multiply by 1 over 1. That's going to be able to be plugged in directly there. And then here, we want to multiply by -1 over -1 to try and plug in for there. And that will help us tremendously. So just multiplying through across for these and knowing that we need to pull out a +1 term, we can essentially rewrite this configuration as 5, because the -1/2 on the numerator here. And then these terms are going to be moved accordingly. But this now becomes -s plus 1. This term stays as s plus 1. And this term becomes the 1/2 s plus 1, based on the 1/2 term that we had multiplied through there. Remember, we are specifically applying each of these directly into our numerator and our denominator. This went to here, while that went to there. This went to there, while this went to there. And then this went to there, while this term went to there. Pretty standard. And so in that way, we've been able to reconfigure and rewrite this based on our +1 notations, where we can see specifically the time functions existing. And so in our zeros, which are the numerator, our zi generality is now -1 over tau with our 0 term, and our poles are going to be based on -1 over tau p, where we can now extract these directly from there in order to solve the equations more rapidly. And what we've done here is we're just describing standard how we would actually extract the time relative to those functions and seeing how we can rewrite this in a more simplified form where we're seeing the relationship between each of those. And so based on these being true for our time constants related to our poles and our zeros, we can actually now explicitly derive these in our notation, and we can use this pretty rapidly for graphical calculations. If we wanted to create a plot about this in MATLAB, we can do so with any transfer function, but this is just one way of representing these. So hopefully this has been informative in walking you through first order systems, second order, and higher order, as well as linearization, where we've been able to use this partial fraction expansion to really help us solve more complex systems rapidly and gain information quickly about the system based on where we might have zeros and stability-based terms. So hopefully this has been fun and informative, and I will see you next time.